Okay, so can you see my screen?
Yes, we can see your screen.
Okay, perfect. I am seriously hoping that no one has tried to join the other one, the everyday link, because that would be a problem. There will be no one there. Yeah, just open the meeting. That would be a great idea. Send the link on WhatsApp if you have a group. I'm pretty sure you have a group. Okay, so do that. There seems to be another issue. Again, I'm sorry for the delay. I am trying to do my best here with limited resources. Okay. Hopefully, this will be it. All right, so I'll share the presentation and we shall start working. Just send them the link. There's a link that I sent by email. Just send them that link. Okay, so in the previous lecture, we spoke about motion in 2 dimensions. We started using the same equations we had from before, but in 2 dimensions. We spoke a little bit about free fall. So today we're going to start with an actual example on 2 dimensions. Share screen. For the love of God, this is a nightmare. Okay, so we will start with a very simple conceptual question, and then we will continue from there onwards. Throwing a ball upward from a moving car. Suppose you're driving in a convertible car, so no roof, top roof open. Your brother is sitting at the back seat, and he throws a ball up. Now, if we assume there is no air resistance, okay, where would the ball land? Will it land behind the car? Will it land ahead of the car? Or will it land back inside the car? Now, remember in the previous lecture, what we said was, when we throw something from a plane, its v in the x direction is the same as the plane. Ahead, back inside the car. ahead, behind. Okay, so we have multiple تعدد الروايات. So what actually happens is, okay, the ball would land back in the car. Now, I know this is not what happens normally when you try it in a car, okay? The reason is we have a air resistance. So what happens is, as soon as we throw the ball up, air pushes it back, so it lands behind the car. You might have experienced it in other forms, someone throwing a box or something outside the window of the car in front of you, and it comes smacking on the on your front shield, on your windshield. Okay. Now, what would happen is if there was no air resistance, we would be having, this is a very, very primary car. Okay. The ball would be going, now this car is moving this way, velocity with v car. Okay. Now what would happen is the ball would be going upwards with vy, whichever velocity you threw it up with, but it would also automatically have also v car. Okay. So since this v car, this velocity in the x-axis and this velocity in the x-axis are the exact same, what happens is the ball will go up and would come back down inside the car if there is no air resistance. If there is air resistance, it's a totally different ball game. Okay? Let's do a numerical example, and it will help us understand a bit more. Let's imagine something that is launched at some angle with some initial velocity v naught. Okay. This is what it's going to look like. It's going to go in an arc. Its velocity, we can write it in vector format as v naught x in the I direction and v naught y in the j direction. So far, so good. V naught x, let's draw it. V naught y. And to find these components, if we are simply told it is launched at velocity 10 at an angle of 50 degrees, for example, just like we did in chapter 2 with when we were looking at components of vectors, we would be getting v naught cosine theta and v naught sine theta to find the components. Okay, let's write them in component format just to be, you know, extra detailed. So v equals u plus at and x and in y. S is equal to ut plus half at squared in x and in y. V squared equals u squared plus 2as in x and in y. Okay. Everyone is admitted. Okay. We reach what we call the equations for projectile motion. Okay. What happens if we have projectile motion? We threw something, okay, and then we left it. In the x-axis, there is nothing to accelerate. Okay, we are ignoring air resistance, so there is nothing to speed the ball up or to slow it down in the x-axis. So acceleration in the x-axis is 0, which means the velocity will be constant, no change. In the y-axis, though, we still have gravity working at all times. No one told gravity to switch off. So we still have a equals minus 9.81 meters per second squared. Of course, this is when the up direction is positive. Okay, so we end up with these equations. Again, there is nothing new. We are only using our three normal equations. V equals U plus AT, S equals UT plus half AT squared, and V squared equals U squared plus 2AS. Nothing changed. We define something called the horizontal range, which is the distance the projectile travels in x by the time it returns to its initial height. And we have an equation. R equals V naught squared over G sine 2 theta. Now, this is the equation that most students end up misusing in one way or another and causing a very, very big problem. What is this equation telling us? It's telling us, if this is my ground level, I am throwing something here at some angle theta. What is my range going to be? How far is it going to go? ما ظاهر العرض. Take the pin off. If my photo is pinned, take the pin off. Okay. It will give us the x-axis range. Now, there's this very, very important thing. It returns to its initial height. This and this need to be at the same level. Okay. So if I have something that starts here and ends up here like this, we cannot use this equation. Okay. If it starts here and ends up here like this, we cannot use this equation. Okay. So R equals displacement in the x-axis until the point where it returns to its initial height. Okay. So a couple of people are asking, can we use other letters? You can use whatever letters you want. There is absolutely no issue. I use U. Some books use V naught. Some tend to use VI. Some use V1. You can use V smiley face if you want. Okay. You don't even need to use U and V. Okay. You can use whatever letter you want. هذه مجرد رموز ما لها أي معنى ثاني. أنت تحدد معنى الرمز أو قيمة الرمز. Okay. So you choose what it means and then you just stick to it. Okay. As a matter of fact, I'm going to be doing that right now just to give you an example. We have our equation, the one I usually write, V equals U plus AT, right? I'm going to be writing it in a totally different way, and mathematically it is still correct. I just wrote it using emojis. Okay. Mathematically, V equals U plus AT and what I wrote beneath it are exactly the same. Okay. It doesn't really matter. As long as you make it very clear and you remember that VI is the same as U or is the same as V naught, or that smiley face is the same as V naught or VI or U, absolutely fine, no issues. Okay. Someone throws a ball A. Okay, Salha throws ball A, Maryam throws ball B. Which one hits the ground first? A, B, do they both hit at the same time, or do we need more information? Ignore air resistance. B, C, A, info, C, B. Okay. So those of you who said need more information are absolutely correct, because what it really depends on is at what velocity are they thrown. But if we assume for a second that their initial velocity is the same, the question did not tell us that, so need more information is the correct option here. But let's assume, for argument's sake, that the initial velocity for both of them is the same. Both of them, so this is theta A, sorry, this is theta B, and this is theta A. And I am going to be assuming that both of them go with the same initial velocity. VIA is equal to VIB. Then what? A, B. So what happens is we need to look at the y component. This is what defines time. Okay, Vy. If, and I'm writing this in capital and underlining it twice, if Vy for A is equal to Vy for B, then they will take the same time. One will be at a shorter distance, the other one would be at a longer distance, but they will take the same time. Okay, but if Vya is not equal to Vyb, then not same time. Okay, if Via equals Vib, they're not going to be at the same time here. Why? Because the angles are different, which means one of them is going to have a bigger y component than the other. Okay. Finally, an example with numbers. A ball is kicked. Let me just see if there are any comments or anything that I am unable to see. No, okay, everyone who wants to be here is here. Let us go back to our slideshow. Okay, a ball is kicked with an initial velocity of 30 meters per second at an angle of 53 degrees with the horizontal. Like so. Anyone who's into football or anyone who's kicked a ball in his life or her life would know this is the trajectory of a ball. I'll repeat. Okay, let's do some numbers. V0, first, let's do it in slow motion. In slow motion, it's going to look like this. Sorry, give me a second. There seems to be an issue. No, no one is emailing me. So, okay. Okay, so let's write it down. V0 is equal to 30 meters per second at 53 degrees with the horizontal at an initial time 0. My initial x position 0. My initial y position, 0. So far, so good. Let's take the components. What is my Vx naught? What is my Vy naught? Well, Vx naught is going to be V cosine theta. Vy is going to be V sine theta. And this is all the information that we have at the beginning. Now the question says, find its position and velocity after 1.5 seconds. Okay, let's do it one at a time. We know we want time to be 1.5 seconds. So it's going to be somewhere here. We don't know exactly where. Let's try it. What more information do we know? We know in the x-axis we are ignoring resistance, so we don't have any acceleration. We know in the y-axis gravity always acts. No one told gravity to switch off. So we will have A is equal to minus G. So be it. So once I do V naught cosine 53 and V naught sine 53, I will get 24 meters per second in the y-axis and 18 meters per second in the x-axis. What just happened? Did I miss a slide somewhere? Okay, there seems to be a problem with the slide, so I'm going to write it down. Let's write it down. Okay, we know our initial velocities. We know we want our final velocities. Which equation do we use? Anyone? I'll write our three equations.
Final equal to V initial plus 80.
Perfect. Okay, so V equals U plus AT. Now remember, X and Y are upset. I cannot tell you how many times students forget this. X and Y are upset. Do not ever mix X and Y. X, Y, Z, these three are upset. They never speak to each other, no matter what. So first thing first, we do it in the x-axis. Okay, so we did Vx equals V cosine, Vy is equal to V sine. We got Vx is 18, Vy is 24. Now at t equals 1.5 seconds, this will become 18 meters per second plus acceleration is 0 in the x-axis. Time is 1.5 seconds. So my Vx is going to remain. My Vx is going to remain 18 meters per second. Constant velocity in the x-axis in the absence of a resistance, which is what we have been saying so far. What about in the y-axis? I'll use the same equation again. V equals U plus AT. Only this time my U is going to be 24. My A is 9.81. And my T is 1.5 seconds. And what I will get will be approximately 9 meters per second. Okay, in this direction and in the up direction. What if I want to find their positions? Well, I will use. Should we always use theta with x-axis? No. The reason we use theta here with x-axis, cosine here, because they told us in the question, this is 53 degrees. Because in the question, it said angle 53 degrees with the horizontal. Horizontal is x-axis. If it said, for example, 53 degrees with the vertical, then we would have done this 53 degrees. Then my x-axis would be sine and my y-axis would be cosine. Okay, so I will draw them both here just to be Clear? These are two cases, they are equally correct. An x-axis should be a equals 0. Yes, you are correct. And the x-axis, a should be equals to 0. And it is equal to 0. And this is why here for a, we put 0. Which is why v initial for x is equal to v final for x. These two are the same. What if you want to find distance? Okay.
Use quadratic equation.
We use the second or third equation. Both are equally fine. Because they wanted velocity and position. We found velocity. Now let's find position. And the x-axis, which one would I use? You know what? I am going to use the second equation just because I am too lazy to do a square root. Okay? I can use the second or the third one, equally fine. Okay? But I am too lazy to use the square root, so I'm going to be using the second equation. Also because it just gives me the distance directly. So S equals UT plus half AT squared. Initial in the x-axis is 18 times 1.5 seconds plus half 0, 1.5 squared. And that would just mean 18 times 1.5, which is 27 meters. What about the y-axis? من وين جبنا 18؟ 18 جبناها من 30 cosine 53. Here, V0 cosine 53. Okay. Y-axis, S is equal to UT plus half AT squared. 24 times 1.5 plus half minus 9.81, 1.5 squared. ليش الجاذبية صفر وهي 10؟ In the x-axis, we don't have gravity. Gravity doesn't pull things left and right. It only works in the y-axis. Okay, and this we get 24.75, approximately 25 meters. Okay, so once we draw the problem and write down all the variables that we have, we end up with a very, very simple substituting problem. Okay?
دكتور
Yes.
لو طبقنا قانون الهوريزونتال رينج ما يصير في الاكس اكسس؟
في هذا you can الرينج وايش بيعطيك؟
نفس البوزيشن.
الرينج بيعطيك الفول distance. Let me show you what would happen if we use the x equation. First, let me just do something. I want to see what would happen. I'm just afraid anyone might still be in the other meeting, in the normal link of every day. Okay. Okay, can you still hear me? Everyone still fine here?
Yes.
Okay, perfect. Okay, perfect. Okay, نصير here. Okay, everyone's here. This is good. What's happening? Okay, it's doing something by itself. I'm just gonna wait until it's done. Do not mess with technology, people. If it wants to do something, you let it do it. Okay. We go back to this, and I will tell you what happens if we use the range equation. Now what the question told us is find the position at 1.5 seconds, correct? Now what we know is the ball left here at time equals 0. What we don't know is at what time did it reach the ground? Okay, what is the time? At what time did it reach the ground? So it could be that at 1.5 seconds, it will be here. And that is fine if you use the range equation. The problem is, say for example, at 1.5 seconds, the ball has gone like this, and it is still here in midair. It's still on its way down, but it hasn't reached. It's still here in midair. So what happens is, if you use the range equation, it might not give you 27 meters. It might give you another number. As a matter of fact, let us try this. Let's try it together. The equation for range is r equals v naught squared over g sine 2 theta. R equals v naught squared sine 2 theta over g. Did I bring it correctly? V naught squared over g sine 2 theta. Okay. Now let's do this. V naught squared is equal to 30 squared over g, which is 9.81 meters per second squared, sine 2 times, what was our angle? 53 degrees? 53 degrees. Can you tell me what is this? 2 times 53 sine of that times 30 squared divided by 9.81, and I get 88.2 meters almost. Okay, so what you get is your range is 88 meters. So at 1.5 seconds, even this photo is wrong. You are barely at 1.5 seconds, you are barely here, for example. So this is the problem with using the range equation to find the x-axis. It only works to find the full distance. It doesn't incorporate, there's no t here, there's no time anywhere. Okay. So find the maximum height it reaches. How do we find this? The maximum height is when it is here, and when its vertical velocity is 0, because if it starts with vertical velocity, say 100, each second it will lose 9.81, say approximately 10. So it's going to go 100, 90, 80, 70, 60, 50, 40, 30, 20, 10, 0 at the very top, and then it's going to accelerate down again, 10, 20, 30, 40, right? So we know that at maximum height, Vy is equal to 0. So what is the maximum height it reaches? We go S equals ut plus half at squared. That's not really useful. V squared equals u squared plus 2as. This might be useful. We know our final velocity is 0. Our initial y velocity is equal to 24 squared plus 2 minus 9.81, and we want to find the distance. If we rearrange this, we get the distance to be equal to what? Anyone? $29.35 is what I get. Which is approximately 29.4 meters to 3 significant figures. Okay. Why 24? Because we already calculated the initial velocity in the y-axis to be 24. So this is all in the y-axis. Vy0, u0, uy, everything is in the y. Okay. So remember, 30 is the angular velocity. We need to find, when we deal with the y-axis, we need to use all the values for the y. When we deal with the x-axis, we need to use the values for the x, not the total velocity. Okay, now the last one. How far away will it reach the ground? This is what you want the range for, because you know you started on the ground, you know you ended in the ground, and all you're not interested in time, all you're interested in is how far away does it go. Here, we already did the problem, and we know that the answer is 88.27 using the range equation. And we already know it's approximately equal to 88.3 meters to 3 significant figures. Finally, find the components of its velocity when it is at a height of 19 meters. Bit complicated. At this time, they don't give you time. They only tell you the height is 19 meters. We know the maximum height is 28.8 meters. We calculated it. Okay, sorry, 29.4. I don't know, this 28.8 is wrong. Never mind. Okay. They want it at 19 meters, so it's going to be somewhere below 29.4. So how do we do this? Well, it's going to be at that height at 2 times. Once on its way up and another on its way down. So how do we find it? Well, we know height is equal to 19 meters. And we have our really nice equation, s equals ut plus half at squared. So what we do is 19 equals, in the y-axis, we started with 24. So 24t plus half minus 9.81 t squared. And what we get is a quadratic equation. Okay, so 9.81 divided by 2 is 4.905. So we get 4.905 t squared minus 24t plus 19 is equal to 0. Okay, and this is a quadratic equation, which if we solve it, we get t1 equals 1 second, t2 equals 3.8 seconds. Okay, we take both of them because both of them are correct. One on the way up and one on the way down. At both these times, at 1 second and at 3.8 seconds, okay, it will be at 19 meters. Because our top is more than 19. It's 29 point something. Okay, so we know at the time, and then we want to know what are the components of its velocity when it's at height of 19 meters. Well, at 1 second, it would be the y-axis would be 14 meters per second. At 3.8 seconds, y is going to be minus 14 meters per second because it's going to be going downwards. But in both cases, our x-axis will be constant velocity, which was what? I don't remember anymore, 18 meters per second. Okay. So this was a long problem, but I'm hoping it was useful. Okay. All right. So the next bit is uniform circular motion. This is a complicated problem and a long problem. It took us almost half an hour to do it here. Okay. Which last point? Okay, so you have something that is going like this, okay, starting here and ending up here. Okay, your maximum height here, say for example, is 100 meters. This is just for example. Okay, and the question asks you, when will you be at 50 meters? Now the answer is, I will be at 50 meters 2 times. I'm starting at 0, I'm ending up at 0. I will be at 50 meters 2 times. Once on my way up, I will cross 50 meters to go all the way to 100. And then again on my way down to 0, I will cross 50 meters again. Yes? So if I use my equation, okay, and I know that I want 50 meters, okay, what I do is I have half AT squared plus UT minus S is equal to 0. I just rearrange this equation. Okay. Now what this is a quadratic equation in T. Okay, if I solve for T, I will get 2 times. The first time will be on the way up, and the second time will be on the way down. Okay. The velocities will, you know, it's positive or negative in one of 2 directions. Okay. One, you know it's positive when it's going up and negative when it's coming down. Or another option is, since you found time, you simply put it in v equals u plus at, okay, where a for u here in the y-axis is minus 9.81, and it will automatically show up as either positive or negative, depending on the time. Okay? So we move on to uniform circular motion. Okay. What is the definition of uniform circular motion? It is motion along a circular path. Wow. فسرنا الماء بعد جهد جهيد بأنه الماء. Okay. Whenever someone is going on a circular path, it's circular motion. But what does uniform mean? Okay. We have 2 things going in circles here. There's something very different between the 2. While both of them going in circles, one of them stops, goes faster, slows down, stops again. On the other hand, this one is going in circles on a constant velocity, never stopping. Okay. Now this one is what we call uniform. The other one we call non-uniform. Okay. We will be focusing on uniform circular motion because non-uniform is too complicated. Okay. Just look at the unable to delete. Just look at the screen. There we go. Let's just look at the movement. Okay, one is continuous, exact same speed at all times. Not exact same velocity, but exact same speed. The other one speeds up, stops, slows down, there are changes. Okay, what is my direction of velocity? Okay, what is my direction of velocity here? Okay, my direction of velocity is dependent on the direction of motion. If I am going this way, okay, when I am at this point, my velocity will be going tangential. When I am this way, again tangential, again tangential, again tangential. Okay. The magnitude of the velocity vector v is constant. So magnitude of v, which is also called speed, is constant, but the direction keeps changing. Okay, it's always tangential. Yes, we finished projectiles. Okay. We will do many more. We'll do projectile problems in the tutorials. Okay, so when we do the tutorial for chapter 4, we will do many problems there. All right. So here's the interesting thing. How did we define acceleration? We defined acceleration as change in velocity. Okay, we did not define it as change in speed. We define it as change in velocity. So although my speed is constant, my velocity keeps changing because the direction is changing, which means that an object moving in a circle technically undergoes acceleration at all times because the direction is changes. Okay, we call this centripetal acceleration, and you might know it from a childhood game. If you ever put water in a glass, okay, and started spinning it around, or you put a piece of rock at the end of a rubber band or at the end of a string, and you started taking it around. Okay, what happens is the rock or the water sticks to the end of the bucket. Okay, and this is caused by centripetal acceleration. The acceleration vector always points towards the center. So now we have two things. Velocity is always tangential to the path, and centripetal acceleration is always towards the center of the circle. I'll introduce a couple of equations and then we'll talk about them. So what is V? What is A? How do we know them? The magnitude of the centripetal acceleration is given by V squared over R, velocity squared divided by the radius of the circle. And that means that the smaller the circle, the greater the centripetal acceleration. So to turn at a large speed, you would need a large centripetal acceleration. And you would, again, if you are used to swirling things around, okay, you would remember that if you have a short string, you need to really spin it fast so that the water wouldn't come out. But if you have a rather large string, long string, you take a very slow motion is sufficient to keep it going. Let me see if I can find a video on YouTube that would help us with this. I know I'm presenting. Okay. Centripetal acceleration demo. Ah, this is good. This is not useful. This is useful.
Imagine you've got a tennis ball attached to a piece of string and you start swinging it in circles. Whoa now, watch out for your buddy. Let's take a closer look at the fascinating physics of this simple action. You've probably heard of Newton's second law of motion as it relates to objects.
Never mind these F equals ma. We'll do these later in the course. Just look at how the motion works here.
Objects moving in a straight line. Turns out, Newton's second law also tells us about the net force on an object as it moves in a circle. When an object moves in a circle, its velocity changes direction. Since the velocity is changing, that means we have an acceleration. And we know from Newton's second law that if we have an acceleration, we have a net force. Now back to our spinning ball. For objects undergoing circular motion, the net force on the object is called the centripetal force. It's a weird sounding word, but it's Latin for the phrase center seeking. It's named centripetal because the centripetal force always points to the center of the circle. The ball has a tangential velocity, so if you suddenly cut the string, it would fly off in whatever the tangential direction was at the moment you made the cut. But assuming you don't cut the string and you keep swinging the ball's tangential velocity is constantly changing directions. This means the ball is accelerating, and the reason it's accelerating is due to the centripetal force. The centripetal force acting on the ball is constantly directing the ball towards the center of the circle, your hand. This, combined with the ball's velocity, keeps the ball swinging in a circle. The same centripetal force that keeps the tennis ball swinging in a circle also keeps roller coasters on the track as they go through a loop-de-loop. So the next time you're having a blast on a roller coaster, you can thank the centripetal force.
Okay, so I like the last bit, bringing it together with the centripetal, with the roller coasters, because this is really, if you have ever wondered why pretty much every single roller coaster is, I'm going to close this, because have you ever wondered why every time you're in a roller coaster, it goes very slowly upwards and then accelerates downwards before going in a circle? The reason is this: you need a high enough velocity and a certain radius to get a good acceleration, okay? If the roller coaster circle is a bit tight, okay, it will, you will face a problem with needing a very, very high velocity. So you will notice something about most roller coasters, okay? If you will notice something that the size of the circle of roller coasters are mostly similar, and they all have something very similar in their design. They make you go all the way up, and then you accelerate using gravity to a very high velocity. Okay. Here's a question. If I have something that is going at a constant speed, okay, how long does it take it to go one circle? Time equals distance over speed, right? Correct? Well, what is my distance? My distance is 2 pi r. My circumference. My speed is constant. My velocity changes, but my speed is constant. So my time is equal to 2 pi r over v. And this is what we call a time period. Okay. We call this a time period. Okay. Okay. Now we started today late. I will try not to finish late also. This will take a rather long time to finish, but Aywa, ask. Yes, no. Okay. لما القنبلة توصل الأرض ولا لما القنبلة ولا وين مفروض تكون الطيارة لما it releases the bomb? These are two different things. اوكي الحين بنحط هذا التسجيل على يوتيوب ويقولوا لنا تعلمون قنابل وما ادري ايش وبعدين بيشيلونه بالجمس الاسود. زين. Okay. Say for example, you have an airplane. This is a very really bad airplane. Okay. Okay. And you want to bomb this location. Okay. Remember, okay, remember that when something, there are two types of bombs: smart bombs, dumb bombs. One that اللي فيها توجيه، اللي ما فيها توجيه، فيها محرك ما فيها محرك. Okay. So we'll take the very simplest of them, which is what I think you're asking about, is what's called a dumb bomb. Okay, which is basically just released. There is no control in it, and there is no engine in it. It's just released. Okay, so what happens is it is released. It is released at this point. By the way, all of this was I'm joking. By the way, this is actually a really, really good question. Okay, and it actually showed up in a couple of past exam papers. Okay, so when it's released, remember, this is very similar to what we had in the previous lecture problem. Okay, so the bomb will have a Vx, which is equal to V plane x, because the airplane is going at a certain velocity. But its initial Vy, V naught y, will be equal to 0. Now, it will accelerate as it is falling down. But so what that means is, the bomb actually never just goes down. Okay, that never happens. What really happens is it goes on a trajectory like this, okay, in an arc. And this is what a guidance system or a good pilot knows when to release the bomb. Okay, so since Vx for the since Vx for the bomb and Vx for the plane is the same, if we ignore air resistance, okay, at the moment the bomb hits here, okay, at the moment the bomb hits the target, the airplane will be exactly on top of it. Now, this usually doesn't happen. What happens is, in reality, okay, in reality, what happens, because you don't want to be in the same area, it's probably a very bad idea. You just released a bomb over someone. They probably don't like you very much, and they would very much like you to, you know, be dead at that point. So what usually happens is, as soon as in the military, they train you, as soon as you release a bomb, get the heck out of there. Either increase your velocity so you're all the way over there, or, you know, or turn around and skedaddle, go back to base. Okay, but basically, if we just assume everything goes on as it is, it will be exactly on top of the location. Okay. Because the airplane is going horizontally. It's not really going up or going down. What's going on? Why is he calling me? Hello? Yeah? I'm still in the lecture. I'll call you back. Yeah? I'll call you as soon as I'm done with the lecture. Okay? مشكلة لما دكاترة وما يفتهمون انك انت في lecture. Okay. لما تطيح من الطائرة تروح بمقدار زاوية 0. Okay, so what happens is, it depends. See, as I said, there are different types. This one takes the very simple physics problem, concerns, you know, the very simple one, which is simply released. So it's usually just released downwards. Nothing happens. There's just a clamp, and it leaves it, and it just falls down like this. But because it has an x velocity, it goes in an arc. Okay. Yes, Ghadir?
Doctor, if they said the rock is thrown up straight from the mountain, maybe, and they want the velocity.
Say that again.
If they said in the question, the rocks thrown up straight, for example, from the mountain, and they want the velocity on the half distance, not in up near the ground, but in the half distance. How can I calculate it?
So if you have something that is thrown vertically upwards, okay, and you want it at half distance, your velocity at half distance, you need to do multiple things. Okay, you need to know what is your V0. 2, you need to know what is your maximum height. Okay, and then 3, you need to do one of multiple. 3, you need to do one of multiple things. Either you use time to find what was it? To find velocity, right?
Yes.
To find velocity, or use distance to find velocity. So what happens is, these are our 3 equations. These are our 3 equations, right? So first you need to find the maximum height. Okay. probably using this equation. Okay. Then you need, once you know the maximum height, you know what half of it is. Okay, so you can either substitute half of it here, or if you have found time, you can put it in here, in this one.
Yes,
Okay.
but if it's thrown from the mountain, from the height, from the mountain, and want the distance, want the velocity, okay, but not the final velocity, the velocity on the half of distance,
Is it thrown up or down?
thrown up.
Okay,
it
so
will-
you're on a mountain, you are here, and you throw up, صح?
Yes.
And you want to know at half distance what's the velocity.
No, the distance when it's returned back to the ground.
Do you is this question in the book somewhere?
Wait.
Let's do something. Send me this question by email, and I will reply to you, and I will also discuss it at the beginning of next lecture. Okay, it's 1:23, which means officially our lecture time is over, but we started late today, so I want to just show you something before we end this lecture, which will serve as the initial what's it called? It will serve as our initial introduction to our next lecture. It's something you know. Actually, you know what? Never mind. We'll just do it at the beginning of next lecture.
Doctor,
Yes?
can I ask you in chapter 3?
Can you ask me what? Sorry, say that again?
Chapter 3.
Yeah, sure. By the way, the lecture is over, so whoever wants to leave is free to do so. Yes.
Example for Karim, if you remember it.
Yes, Maisa, 2 and 3. The example for Karim, was it in the previous lecture? Chapter 3 was 2 lectures ago.
2.4, I think. No, the same lecture for 2.4.
2.4.
Yes, in the same lecture.